Alrighty, so hello everyone. My name is Amira Ruby. My partner is Reese Welty, and today I'll be presenting our chemistry project. To start off, I want to tell you guys all about our objective. Well, we want to compare the differences between mercury 2 fulminate and mercury 2 cyanate. Now, the differences between the two is their ions. Within the ions, they have different central atoms. Now, this can determine their stability, formal charges, etc. So within the fulminate ion, there is the central atom of nitrogen, as you can see from this key below. And within cyanate, the blue is carbon. And once again, these differences of the central atoms change everything. So now moving on, I want to talk a little bit about their Lewis structures. So for the Lewis structure of fulminate, here you have it below. It is CNO minus. Now, when determining the Lewis structure, we first think about the total of valence electrons, and that is 16. We get that by calculating each valence electron of themselves. So for carbon, there is 4. Nitrogen, there is 5. And oxygen, there is 6. But how does this add up to 16? Well, we add a plus 1 because, like I said before, it is CNO minus. And this minus has to be counted. And I'll explain a little bit about how we determine this to be the Lewis structure versus their resonance structures, which are the different changing ways that they can have varying bonds. And I'll show you that below. So here are the different formal charges and resonance structures for fulminate. You can see that there are different triple bonds and single bonds between the carbon and nitrogen versus there's double bonds between carbon and nitrogen and oxygen. And then there's one single bond between carbon and nitrogen and then a triple bond between nitrogen and oxygen. When determining which resonance structure is the most stable, we look at their formal charges. The way to calculate formal charge is by subtracting the total valence electrons by the sum of the lone pair electrons plus 1/2 of the number of bonding electrons. So one example, we can talk about the carbon here. We know, once again, carbon has 4 valence electrons, and we would subtract that from the total of lone pairs, so these are these little 2 dots. So 2 plus 1/2 of the bonding. And so now we see that there's triple bonds here. And within each bond, we can imagine there's 2 dots. So subtracting that would be, well, really it's 6, but dividing that by 2 is 3. So we put a 3 here. So now it's 4 minus 5, and that means a formal charge of -1. And that is much better than the formal charges of -2 and -3 here, because we don't really want too many high formal charges, if not that, messes up with the stability of the molecule. So we know that these were wrong. And once again, you can't just do the first formal charge and then determine which resonance structure is best. You'll need to do that for all the other elements as well. So there you have it. And now moving on to the Lewis structure of the cyanate ion, which is here below. The main difference is the, once again, central atom. The carbon is in the middle. The way we knew that carbon should be in the middle is, well, because it's the least electronegative. And then when determining which one had the triple bonds, or the bonds between the central atom, we looked at which one would be more likely to give up valence electrons. And we knew it would be the nitrogen because it's less electronegative than oxygen. And once again, this molecule or this ion has its own resonance structures. So here below are the 3 different ones. We have different bonds. Well, right away, once again, we do the formal charges. And one way I said it before is by doing 1/2 of the bond plus lone pairs and subtracting that from valence electrons. Another way we can do that is just by doing the valence electrons minus the bond pairs. It's just another way of saying it, besides saying, like, imagining the dots and splitting that in half, by just seeing the lines and counting those as 1. So what I mean by that is, let's take this nitrogen here, for example. Okay, So nitrogen, we know that there are 5 valence electrons. So that's total, minus, and then we'd add the bonds. So we see there's 1 here, so we just do 1, plus, and then we count the dots itself. So 1, 2, 3, 4, 5, 6. So really, this is 5 minus 7, which gives you -2. So I want to tell you why this Lewis structure, or this resonance structure here, is not good. Well, we know for sure it is not going to be stable because of that high formal charge of those -2. So right away we can just take that out, exit it out. And now we're left with these two. But the question is, do we want to have the negative charge on the oxygen here or on the nitrogen? And well, the answer to that is we want it to be on the oxygen. Reason being is because it will be more stable. Oxygen is more electronegative, so it can handle the negative charge, which results in the triple bond here that we had seen before in the Lewis structure. Okay, so let's clear that. And let's move on to stability. So after comparing the two, we can narrow down why one is more stable than the other. Fulminate is very unstable. It's okay, it's doable, it's here in nature, it does exist, but the reasons why it's unstable is because it has a high formal charge, it has a negative formal charge on carbon, and a negative formal charge on nitrogen, as we had seen. And usually we want those to be a 0, which is what we see in the cyanate. And the reason why cyanate ions are stable is because the negative charges on the oxygen, like I explained already, it is very electronegative, so it can handle that negative charge. And then there are low formal charges in general. We can see that there is the -1 on the oxygen, 0, 0 on carbon and nitrogen. So that makes it very good and stable. So now moving on to rule violations. The 3 types of rule violations is odd electron molecules, and that is when there is an odd number of valence electrons within the atoms. And within the atoms of the molecules, and that violates the octet rule. Another way is within the electron deficient molecules, and those are the ones that don't have the total of 8 adding up within each atom. And then there's the opposite, which is the expanded valence shell molecules, and that's when each atom has more than 8, or not each, but one or more of the atoms themselves have more than 8 valence electrons. Within our 2 molecules, the fulminate and the cyanate, we don't see any rule violations. Each atom has their own 8 valence electrons, and they work. Now moving on to the molecular and polarity of the 2 molecules, or molecular geometry. Well, by looking once again at the Lewis structures, we can see which central atoms have lone pairs and bond pairs to determine the geometry. While comparing the two, we can see that the central has 2 bond pairs. And you might be saying, well, there's multiple bonds here. You see those triple bonds and the double bonds, right? Or single bonds. Well, each bonding region counts as 1. So if you see a triple bond, that counts as 1 region. So that is why you see 2 different bonding pairs or regions. As you can see here, 2, and then 2 again here. And lone pairs are what you would see with the dots, which you don't see here in the central atoms, which is what you take into consideration when determining the molecular geometry. And so when we have 0 and 2, which is for both, then we can determine that the molecular geometry is linear. And then once we figure that out, we can put it into like a 3D form and just imagine it. And then we would cut it in half. And by seeing if it's symmetrical or non-symmetrical, we can determine if it's polar or non-polar. And in this case, the 2 are polar. So that is for the molecular geometry and polarity of the 2 molecules. So now let's talk about, if I can move slides, the physical and chemical properties. So for mercury fulminate, some things we know is that it's gray, pale blonde, brown, or white powder. It has a molar mass of 284.624 grams per mole. We know some things like the melting point of 160 degrees Celsius. It's slightly soluble in water, the basic things. Whereas mercury cyanate, some things we know is that, well, it's a mercury salt and the molar mass is 284.63 grams per moles. There wasn't really too much about this molecule. Reason being, most likely because I honestly, I actually don't know. But one thing we could do is make an educated guess. So my partner and I looked into the percent composition of this element, or of the elements within the molecule. And we noticed that actually mercury takes up a lot of the percent composition. It has a whopping 70%. So we were thinking about, well, if it has so much of the mercury, then could we see a correlation between the mercury element within the actual molecule? And so one thing we know about mercury, for example, is that it's insoluble in water. So that could possibly make the molecule itself insoluble. But maybe if it's mixed with the other elements, it could become slightly soluble, which would be similar to the mercury fulminate as we saw here. So just thinking about the elements and what we can know or what we can guess, of course, with research, then we started to think about different physical and chemical properties. So that is basically it for our presentation. I hope you guys enjoyed learning about the differences between mercury 2 fulminate and mercury 2 cyanate. Thank you so much, and I look forward to hearing about what y'all have as well. Thank you.